Okay, today we are going to discuss about the Microprogrammed Control Design. What we will do is we will take up an example and go through a very structured design procedure. I would like to emphasize here the reason that we are identifying the steps and going through the procedure is almost any design problem in real life, unless you break it down into parts and solve it, neither the solution is verifiable nor you can be very confident of what you have produced is going to work. So it's important that you look at the steps and try to follow the steps in doing a design. And the approach that we are doing, because it's a Microprogrammed Control Design, it's a very structured type of an approach where we will be able to identify very clean specifications of even the subcomponents. Okay, so let's go through the steps of this and we will follow, we'll take up an example and go through the same steps as we have listed here. So first we do the design the data part and identify the control and status signals. This part is going to be based on your algorithmic description. You have to know what are the operations you need to perform, how are you going to store the data that you have, and then you will do the data part design. And the important thing is, from this you will also identify very clean interfaces between control and data in terms of the control and status signals. The next step is to design a microsequencer based on the branchings required. We will talk about this. If you look in terms of a state machine, or even if you look at your algorithmic description in any other manner, you can identify what are the, and of course the status signals are the ones which are going to result in state transitions. It's based on these status signals you either go to this state or to some other state, or execute one part of the algorithm or some other part of the algorithm. So they actually define what is the type of branches that are required, and they are going to influence the microsequencer. Once you have this, you have from the schedule of operations, finalize the size of the control ROM. As far as the control ROM is concerned, it is only the size which is going to define the component. Of course, the contents of the ROM, but that's the last stage. But first we have to know what the size of it. Because the size is also going to influence things like the address lines and so on, and would have an influence on what the microinstruction format is. This will be followed by design of the microinstruction format, and finally we will have to generate the microprogram which will be put into the control ROM. So we will follow this procedure. We will take an example and do that. But in the subsequent lectures, we will also talk of optimizing some of the components. So today's emphasis of today's lecture will be just to achieve the goal that we want and not really bother about whether the solution is optimal or not. We will take up some of these steps can in turn result in a cheaper solution in terms of the area or the cost of the design, and we will look at those options later. So the example we will take is the same example that we had before, because we don't have to spend the time in understanding the algorithm itself. We already have done this GCD computer as part of the design that we talked of the state machine. So we will take the same example. The data part also will be similar, and we will just to refresh. So we have two inputs which are, let's say, 16 bits each. It doesn't really matter here, you can take 16 or 32. Some 16-bit inputs, two positive numbers, integers, then the result is a positive integer z. And we have a start signal which makes this component start the computation, and I indicate through an end of computation signal that the GCD has been computed, and the value that is present here is a valid GCD of x and y. So that is the algorithm that we follow is the same algorithm that we mentioned before. The only changes that I have made is I put a couple of statements. So one statement over here, wait till start equal to 1, essentially is what we had later on introduced, waiting for the start signal before I start the computation. Once I wait for the start becomes 1, and then I follow it up by inputting the input values, and at the same time I set the end of computation to 0. Because computation has started, so the value now, the computation is going on. So now I say while x n equal to y, I repeat this, and then greater than y, I subtract it, and then subtract the smaller value from the larger value, keep on repeating it till both of them become equal, and that's the GCD. I transfer the value into output, set end of computation to 1, meaning that my computation is over, and go back to the startup. Again, my component is waiting for the next set of values to be input for computing the GCD. So this is a fairly straightforward algorithm, and we again look at the data path for doing this, because the first step, remember, keep these steps in mind. So the first thing that I will do is to design the data path. So the data path is same as what we had before. I use 3 registers, R1, R2, R3. R1 to store the value of X, R2 to store the value of Y, because they are coming from the input, R3 to store the value of Z, subtract to perform the subtractions, and comparator to perform the comparisons. So now as far as the control signals are concerned, let's look at the control signals. R1 is to get 2 inputs, so I need a multiplexer. R2 is also going to get 2 inputs, I need a multiplexer. Again, subtractor, if I assume that I can only subtract this operand minus this, so then again I need to get 2 inputs from R1 and R2, and I need the multiplexer. So if you look at the control signals now, I have, so select R1 is one control signal, select R2 is one control signal. These are the control signals that are going here. Select subtract 1 is one control signal, which selects the operand of the first operand of the subtractor. Subtract 2 is the other control signal, which selects the second operand of the comparator. Now apart from that, I will have all the load signals, load R1, load R2, load R3. Then I need to have clear and preset signals for this. So I will have clear EOC and preset EOC. So these are the control signals that we have identified. Of course, I have not shown the interconnections. You can complete the interconnections that are required. So R1 output will go to one input of the multiplexer, and this input of the multiplexer R2 will also go. And as far as the status is concerned, so we have 3 status signals. One start bar, which is coming from external to this, so that's also going as a status. Another is equal, another is greater. I have 3 status signals and 1, 2, 3, 4, 5, 6, 7, 8, 9 control signals set. So this is the first part of it, and I have very clearly identified my data part. I have identified the control as well as the status signals. Of course, I don't have to necessarily in a microprogrammed control go through a state machine, but because we have already understand how the state machine works, so let me go through this particular phase. Otherwise, you can directly analyze the algorithm and go to the second step that we talked of. But let me look at the state machine, and now what I will concentrate is what are the type of branching that I need to support, in the sense that I need this. And here I am going to test in 2 phases. So it is, if this is equal, then I go here. Then if it is equal bar, I go here. If it is greater, I go, let's say, here. And if it is, I go here. So I am doing a, remember in my state machine implementation, and this is one difference that I have pointed out between the microprogrammed implementation and state machine, that typically in a microprogrammed implementation, you do not do more than 2-way branching. In state machine, it really doesn't matter, you can do multi-way branching. Of course, sometimes if it is very critical in microprogrammed also, there are mechanisms to do it, and we will talk about later on when we talk of sequencer designs, how we can support multi-way branching. But the typical microprogrammed control, you only do 2-way branching. And also, the reason I mentioned in terms of there is something about the state encoding, I am going to translate each of these states into a microinstruction. each state of the state machine is going to, and the way I have written my control signals, you can see that what I am trying to do is, okay, this part will be clear from the next, we will come back to this. So once I have noted down these control signals, now I can primarily identify what are my control flow requirements which my sequencer needs to support, and that has to be very clearly identified. So what I have is, I have three types of control flow requirements which my sequencer needs to support. My sequencer should be able to support next microinstruction, implying that if I am executing the ith microinstruction, I should go to the I plus 1 microinstruction. It's called next, or it's also called continue, means continue with the execution. So if you have to execute a sequence of microinstructions, you should be able to use this next microinstruction too. So this is a control flow requirement. So if this you can either identify, as I mentioned, from the algorithm, or you can identify from the state machine. So now the other type of control flow is, I have to be able to test a condition, if condition, and then I go to some microinstruction mj, as I go to mi plus 1. Implication is, I need to translate, because see, if I want to perform a, just like in a program, if you want to perform a jump, you have to specify that address that of the instruction that you have to go to. Similarly, in a micro instruction, you have to specify the address of the micro instruction that you want to jump to. So now I don't want to specify more than one address. The other address is by default, if the condition fails, the other address is by default the next micro instruction. That is why I said an if condition then mj else mi plus 1, where I am executing the mith instruction. What I am executing is the ith instruction, and then I go to this. And the conditions that I have to test are start bar, equal, greater than. These are the three conditions that I need to test over here as part of my sequence control. And with each of any of these conditions, I should be able to support this type of a branch. Then I need to have go to my instruction that I want to address, I want to specify. Let me look at my state diagram and identify where do I need this control flow requirements. Where do they originate from? If you look at this, I am going to now, I am looking for the start bar. So basically, if you look at implementation of this in a microprogrammed control, this will be if start bar, then S0, continue to do S0, as you go to the next micro instruction. Because S1 is going to be placed, even in terms of the micro instruction addresses, S1 is going to be placed next to S0. So I will have to specify only the address of S0, whichever is the micro instruction address for this, as I go to the next micro instruction, which is S1. As far as S1 to S2 is concerned, there is no condition to be tested, so this can be a continue on the next micro instruction. I can just go to the next. When you come to S2, if condition is true, the condition to be tested is equal. If condition is true, then I go to S6, else I go to the next micro instruction, which is S3. Similarly, when you come to S3, if condition is true, then I go to S5, else I go to S4. Please remember, here there has to be compatibility required because I am only specifying one. So that's why I am testing here start bar, I am testing here equal, I am testing here greater, and I am placing them. If I interchange S4 and S5, then I have to test greater than complement of that rather than greater than itself. So once I have this requirement, so then I can very clearly say what is the microsequencer specifications I require, and identify what are called microsequencer instructions. So here I have identified three microsequencer instructions. Next, conditional jump, unconditional jump. What is the meaning of these three microsequencer instructions? These are the instructions which will be part of the present microinstruction format. And this are going to control how the sequencer is going to work. So implication is, if you consider the sequencer itself, As I said before, the role of the sequencer is to generate the next address. This is your microsequencer. This one? Okay. So here what I have identified is identified these three instructions. These three microsequencer instructions are nothing but they directly follow what are the requirements of my control flow. My control flow requires that I should be able to execute the next micro instruction. So then I will have this next as a sequence control for it. I should be able to do a conditional jump or a conditional branch, and for that I need a conditional jump microsequencer instruction. I should be able to do an unconditional jump, and I need an unconditional jump instruction. These are very clearly part of the requirements that come from this. There's just a one-to-one mapping of this. I had these three, and from these three I identified. So how does these three instructions work? How do they work? So this is what I was trying to explain in terms of the microsequencer itself. Microsequencer gets a microsequencer instruction. How many bits it gets, of course, depends on how many instructions I need to support. In this case, I need to support 3 instructions, so I will at least require 2 bits. I can also use 3 bits, I can use 2 bits, depending on how I encode them. Now, apart from that, it also gets something else. It gets the branch address or the next address. Next address, of course, is generates. Branch address is the whenever you are doing a conditional branching or whenever you are doing an unconditional branching, I need to generate this branch address. Get it? We will talk about what the size of this in a moment. The other thing it gets is a condition. So based on these 3, branch address, condition and microsequencer instruction, this generates the next address from the present address. Previous address is not the input, this is the input. If I want to do a branch, previous address is stored internally. See, for example, if you talk of a condition, I need the next address that I need to go to. So this J part has to be supplied externally. I plus 1 I can generate internally because I know what the previous instruction was. So I plus 1 can be generated internally. Similarly, when I want to do an unconditional branch, I have to supply this I over here because I need to. So these are the branch addresses that I mentioned. This is a branch address, this is a branch address. Here, of course, the branch address does not mean I will actually go and execute J. It will depend upon my condition whether I go and execute J or I continue with I plus 1. Here, there is no choice. I will execute. So these are the 3 inputs to the microsequencer: the branch address, the condition, and microsequencer instruction. And the design of this microsequencer itself, which we will customize, we will take up later. But primarily, the specification of this microsequencer should be very clear. Because once the specification is clear, I can design this also as a component that I need. The way the microsequencer is designed is you can talk in terms of customizing a generic microsequencer. Basically, there are only few options, and from those options you can choose and you can also size them depending upon your requirement. There is a requirement for sizing this, and these 2 are equal typically. This corresponds to, this will come from the size of your microprogram because this is being fed to the control ROM. This is being fed to the control ROM as an address. So this depends upon the size. This depends, of course, this is just one condition. I will do the multiplexing, I am doing it outside. You can also consider it to be inside or outside, but here I am doing the multiplexing. And the size of this is number of status lines. I need to do a status select. There is a multiplex. And this I will get as a condition which is going to be the input to this. If you now look at the overall block diagram and try to understand these things before we start designing the microinstruction format itself. So let's get back to the, these are the set of control signals which we have identified in this case to be 9 of them. Yes. These are the status lines which are coming from the data path. Okay, this is coming from the data path, and I select one particular status line to perform a conditional jump. So please remember, when I say if condition, then mj else mi plus 1. Okay, so I am choosing a certain condition, and what condition I am choosing depending on which state I am in. So if you talk in terms of the state diagram, so of course I am going to have an equivalent micro instruction for each of the states. So depending on at this particular micro instruction which condition to be tested, I can select it. But once I select it, that particular condition will come as an input to the microsequencer. One of the status lines will come as the input to the microsequencer. And depending on which condition I am testing, so only that I will get here through the giving a proper input to the status select. And once I get that particular condition, I can have a conditional jump instruction over here to decide either this goes or the next instruction goes, which is the. This point will be clearer. I can clarify it again once I write the microprogram for the example that we have taken. So I have this control signals 9, and I have this status signals which are 3 for this particular case, size of this. So I can decide what? I can decide on this S. I can decide on the size of S. Okay. What will be the size of S? I will at least require 2 bits to select among the 3 status signals. This will be the size of S. Size of M is already 9. The size of K. K gives me the sequencer instructions. And we have 3 sequencer instructions, so this will be 2 bits. There is a sequencer instruction, and because I have 3 choices, I have to choose between from 3 of them, so I will require at least 2 bits. Now the only thing that needs to be decided is n, and n is going to be determined by the number of address lines that are required. Number of address lines that are required is determined by the size of the control ROM. The size of the control ROM is in turn decided by the number of micro instructions you have. Okay, and because for each state I am going to have one micro instruction, and I started with having 7 states, and this particular example I don't require, I can just map a state to a micro instruction. So I will require 7 micro instructions. That means I will have a size of n to be 3, which is nothing but the log of the size of the number of micro instructions. So I have, and this n is also 3. So now this completes my IO design of this, like I input output design of this. This I have 2, this of course is 1, this is going to be 2. Of course this doesn't come from the sequencer, it comes directly from the micro instruction format. We will see that. This one is 3 and this one is 3. I need to generate 3 next address lines based on 3 branch lines, 2 microsequencer instruction and 1 condition. So I have a clear specification of my sequencer, and I have clearly identified the sizes of all the interconnections here. I still have not designed my sequencer. I will design my sequencer later, but first I have decided on the specifications, the requirements as say for each one of them. Let me go to the microinstruction format. I am essentially repeating. I listed down what and all I have been talking about till now. These are all the control signals that I have. Select R1, select R2, select subtract 1, select subtract 2, load R1, load R2, load R3, clear EOC and preset EOC. These are all the control signals that are going to the data part. They are signals which are required by the control part itself. These are the control part signals. I need the sequencer instruction which is 2 bits. I need the condition select which is 2 bits. I need the next address. Okay, I should say branch address. Branch address which is 3 bits. And of course, I have 3 status signals coming as an input. They are not part of the format, The format actually ends here, but they are coming as. What is the implication of this? The implication of this is, please remember, when we talked of the microinstruction format in the last class, we said there are various components of it. These are the control signals. The control signals in this case are 9. I have the microsequencer instruction, which in this case happens to be 2 bits. I have the condition select, which also happens to be 2 bits. And I have the branch address, which happens to be 3 bits. So this is my microinstruction format. It consists of 4 components over here. And total size you can see is 16 bits that is required. 7 plus 9, 16 bits that are required for this. This is now the next step that is required is I have to define my encoding. I have 3 microsequencer instructions, and I have 2 bits to store them. So I have to say what is 00, 01, 10. So I can say 00 is next, 01 is conditional jump, and 10 is jump, unconditional. I can of course choose any other encoding. My microsequencer should be compatible to this. This is whatever I design should be compatible to this. That's what is required. It's not critical what coding I choose. The complexity of course of my sequencer, the logic that I require would be different if I choose a different encoding. Conditional select, I need to select from 3 conditions. So I have to say what is a condition. So if I say 00, what's the condition? 01, what's the condition? 10, what's the condition? 11 again is not going to be used. So 00 here will let us say the condition is start bar. This one is equal to, this is greater. What is the implication of this? Implication of this is that the multiplexer inputs that we are connecting the status signals, they should be appropriately chosen. They should be compatible to what I have. So I have this multiplexer. Zero, 1, 2, 3, and this is my condition. This is my condition input that's going to the sequencer. So if I have chosen this, then I should connect this to start bar. I should connect this to the output of the comparator. So these connections, and of course this connection is not used. So when I am choosing this, what I am influencing is how I am going to connect the inputs to this multiplexer, because these 2 bits are going to be used as my condition select. So these interrelationships should be clear. Of course they are obvious, but one needs to be clear that how the interconnections are going to get completed in this diagram. So this is the overall basic diagram that I am trying to complete. I already designed my data part. I have designed my multiplexer because based on my condition select input I have designed this. The register size, I already know my register size once I know my W. W in this case happens to be 9 plus 2 plus 2 plus 3, so that is 16. So I already have a 16-bit register, so I have the specification of this. Once I have my microinstruction format defined, I will now be able to complete the specification of my ROM. My control ROM, I already had the number of words. The number of words was 7 because I had the states as 0 to 6. So this will going to be 7 by 60. So I have designed all my components, except I have not designed the internals of sequencer, but I already arrived at the specification of its inputs, outputs. I already designed what my sequencer instructions are going to be. and I have already decided what the number of branch address lines and extra address lines are going to be. So we will talk about the sequencer design later on. Let's first complete the microprogram. So I have a symbolic microprogram which I can now write. Even without bothering about the internals of the sequencer, I can write the symbolic microprogram. I am directly converted. Basically, this microprogram is nothing but conversion of that algorithm and the state machine into a microprogram. Each of the states that you had is going to get a mapping directly into a microinstruction, and in the same order, M0, M1, M2, M3, M4, M5, M6. And I am writing all the actions that are required to be performed, all the micro operations that need to be performed in each of these micro instructions. If you consider the M0 instruction, micro instruction, what is really need to be done is, I need to just check the start signal. So I choose a sequencer instruction to be conditional jump, and I choose the condition select, whichever condition is to be selected, I choose to be start bar, and my next address is 0. The implication is, I will be, if start bar is true, that means start is false. If start bar is true, I will continue to be in this particular loop. But if this particular, I execute the else part, if start bar is false, that is start is true, then I will go to the next microinstruction. I am not performing any data operations here. The whole thing is only a control operation. I go to the next microinstruction. The next microinstruction, I will come only when it is start. And the next microinstruction, what I am going to now choose is, what I am going to do is I am going to load the registers R1 and R2. So select R1 to be the X input, select R2 to be the Y input, load R1, load R2, clear EOC because I will now start doing my computation, and sequencer instruction is continue because I am just going to go to the next. Please see that in each micro instruction, I am not writing all the fields. I am not defining all the fields. Each of the fields also has a default value. We will talk about that. We considered this, started talking about it last class. I will re-emphasize that. So what we are assuming is, for all the fields which are not defined in a certain micro instruction, the default values are takes over. We will discuss that. So next we go to the next micro instruction. Sequencer instruction is conditional jump because what I am doing over here now is doing this. At S2, conditional jump, conditional select is equal and next address is 6. So if equal, go to 6, and this is this particular branching. If equal, go to 6, else go to the next microinstruction. Okay, now there are certain issues that are related to the timing and the way the circuit operates, and these are extremely important in the design. Why can't I do this operations sequence? After all, here I was not doing anything as far as the sequencing is concerned. I just had continue over here. Why can't I push this over here? That means, in terms of timing, in terms of the state diagram, that means I can perform the branching right over here. Instead of performing the branching here, I can perform the branching right at S1. This is all related to our timing, the way we have designed our circuit in terms of the timing model. Let me just clarify this again. If you consider the clock, so nowhere we are discussing this as far as the design is concerned. I am having an implicit model of timing, and that should be very clear what the timing model is. What I am assuming is all actions, all state transitions, all loading, everything is taking place at the rising edge. You can assume everything falling edge, everything will remain same. So during this time, there is going to be a certain micro instruction. And if I give a load signal the load is a synchronous load, and at the end of this cycle, the loading will be performed. All loads are going to be performed. So this is my load signal that, let's say, is going to appear. Let's say load R1. R1 will be loaded over here. So the implication is, when I am doing my microinstruction M1, when I give load R1, load R2, is at the end of the cycle corresponding to microinstruction M1. If, let's say, microinstruction is M1 here, this is the microinstruction M1 over here. At the end of it, my registers will be loaded with value X and Y. Of course, the issue is why at the end? Why can't we do at the beginning? We will clarify this next time when we come to the next instruction why this is required. So now, output of this, if you consider your data path, the output of this is going to the comparator. And my comparator will require some time to compare. My clock cycles are so designed that basically the two most important delay elements as far as my data path is concerned is the comparator and the subtractor. Both of them are 16 bits, let's say, wide. All our operations are 16 bits, so please remember that both this comparator and subtractor, the delays, if it is a ripple carry type of a circuit, it will take time proportional to number of bits. So there will be substantial gain delay in both the subtractor and the comparator. So I have to leave one clock cycle for this comparison operation. So though I am not specifying anything here in terms of M2, in M2 I am only specifying only the control. The reason why I am only specifying the control is the comparator inputs are hardwired. If I had multiplexers at the input of the comparator, I would have to use those multiplexers to get the proper inputs to the comparator. As far as my data part is concerned, comparator does not have. So comparator is always connected to R1 and R2, and it will take a clock cycle to produce the output. If there has been a multiplexer here, I would have to choose that multiplexer to get the proper input to compare in M2 itself. That will happen at the beginning of the cycle, and by the end of the cycle, the comparator would be ready. So this timing model is something which you should keep in mind. And this is a simple model that we follow unless otherwise mentioned, that all actions take place at one edge, and all delays are such that they will be less than equal to the clock cycle delay. So I am performing this comparison. So when it comes to this, so I go to M2 to M3. Actually, there is really no time that was needed because actually the inputs are not changed, so the comparator should have been ready. But because we cannot specify two addresses in the same microinstruction, I have only field for specifying only one microinstruction address. So I am breaking this into two branches. First I check for equal and then I check for greater than. So this is also my sequencer instruction. So here the limitation came from by microinstruction format because I cannot do a three-way branching. I have to break the three-way branching into two two-way branchings. So I come over here, I check whether it is greater than. If it is greater than, then I go to. Okay, so there is a mistake here which should have been 4 and 5 because if R1 is greater than R2, then I have to subtract R1 minus R2. So this. Otherwise, if it is not greater than, then I go to the subsequent one M4. And here what I am doing is I am choosing the subtractor 1 input to be R1, subtractor 2 input to be R2, load R1. And now remember why that load thing was required at the end. You can see that in this case no operation was being performed. But in this case, at the end of the clock cycle I need to, because subtractor will take time to subtract. So I have to have the clock cycle delay to perform the load. Previously I was just loading, the delay was only through the multiplexer. Here it is not just the multiplexer but also the subtractor. So this whole path, I am going to choose now R1 as an input, multiplexer, subtractor, R2 as an input, multiplexer, subtractor, and this, so one more control signal is missing here. I should have select R1 for subtractor because I need to select this multiplexer as well to go to the R2. Input multiplexer. Similarly here I need select R2. subtractor output has to be the input over here. So I need to have all these data, and apart from the data, I also need to do the sequencing. Each microinstruction typically consists of data control signals and the sequencer control signals. In this case, the sequencing required is unconditional jump. Go back to your state diagram. I need to perform these jumps. I need to go to S2 and there no condition being tested. So I will have sequencer instruction to be jumped. And my next address, branch address. My branch address should be specified to be 2, branch address should be specified to be 2. Now I go to the next one. So if both of them are equal, I will come to S6, M6, microinstruction 6. I will preset EOC, load R3, sequencer instruction jump, and branch address C. This corresponds to this particular transition. So all my transitions have to be supported by sequencer instructions. That is the primary thing. Once I have this symbolic microprogram, now I have to convert it into a binary one. And where will this go? This will go as the control ROM. So I have my control ROM now, which is nothing but 16 by 7. So I will have 16 columns. I am not drawing all of them, you can fill this up. I have 16 columns and I have 7 rows. And this table needs to be filled up based on the symbolic microprogram. And once I am filling up this table, only thing I want to say is, I have not specified all the 16, for all the information corresponding to all the 16 bits in all the micro instructions. For example, if you consider here, when I say sequencer instruction is continue, I have not specified what condition select is and what next address is, or branch address is. I have not specified this. I have field for this. Condition select, sequencer instruction, and branch address. This is my address is 0, 1, 2, 3, 4, 6. Similarly, I have fields over here. So I have fields for all the loads. Load R1, R2, and so on and so forth, and select. So when you consider this, I can directly now I can use this information and I can use the information that I had before in terms of my encoding, and I can directly write my 0, 1 pattern that I need over here. So let me convert it for the first couple of them and then it's clear. So for example, conditional jump sequencer instruction is 0, 1. Condition select is start, so that is 0, 0. Branch address is 3 bits is 0, 0, 0. If I go to the next one, so this is, as for the next, that is the continue instruction, continue is 0, 0. And here, I don't care, once I am selecting that I am going to go to the next instruction, I don't care what this conditional select is going to be. Then for the 6th instruction, it is jump, unconditional jump, it is 1, 0. Conditional select is this, but this is to be specified. I need to specify this. For my micro instructions 4 and 5, again I need to specify this. I don't need this. I need to specify this, which is 2. And for this one is sequence 0, 1, I need to choose equal. Equal is 0, 1. And if it is equal, I go to 6. Next one is 0, 1. I choose greater than. I go to 5. And this is a control part of it. I can fill up all the 9 bits corresponding to the data part. And when it comes to the data part, the loads, if you are not specifying a load, it should be 0, because I don't want to load any arbitrary value into a register. If you are not specifying a multiplexer select, it can be don't care. So the default value for multiplexer selects is don't care. Default value for all the load signals is 0. Similarly, default value for all clear and preset signals is 0. So once we have done this, we are completed. If you consider the block diagram that we had, we have now filled up everything that we wanted. Next is we go to the next microinstruction. When I am saying next or continue, that means if I am executing microinstruction 1, if I have next sequencer instruction, that means I will go to 2. I can replace it. The question is, you can actually replace this next by an unconditional branch. You can, instead of doing this, what you can do is, you can say it is 1, 0, and you can replace it by but the problem is, to do that, if of course in this particular example it doesn't make much difference because there is only one place where don't care is coming. But if you have a large state machine and there are a lot of edges in your state machine which corresponds to just going to the next microinstruction, if this has a lot of don't care, that will help me in reducing actually the width of this microinstruction. We will consider this, I will come to that point. Let me first answer the other question that was regarding the timing. That timing that we had discussed, silence please. The timing that we had discussed was corresponding to what we said was all my load operations, all my state transitions are at the trailing edge. That is, if you consider this to be a clock period, it happens at the end of the clock. And all this time is available for all the combinational delays that you have through the multiplexers, through the subtractors, through the comparators. And if you follow this model consistently, all your operations will work. Because what you are saying is, whenever say a particular microinstruction comes, if you say that the select for R1 is X, what it means is the select R1 will come and the multiplexer will immediately get that control input and that X will start flowing into the input of the register R1. But the register R1 will latch or will trigger or will load the value only at this edge. So it will have a stable input. All your setup time requirements, everything will be taken care of by the delay of the clock period. Similarly, when you are doing subtraction, what you are saying, yes, selecting the input to the subtractor, multiplexers, performing the subtraction. There is no control signal for performing the subtraction. The subtractor unit is only performing one operation, so it doesn't require any control signal. It directly performs the subtraction. Output of it goes to the input to the multiplexer for R1. It flows through the multiplexer and becomes available to this at the end of the clock period. So the model is at the end of the microinstruction we are doing. Now let me motivate what is it that we are going to do now in the next couple of classes. What we are having now is, one thing that we are left is design of this microsequencer itself. We have arrived at the specification of the microsequencer. We decided what this microsequencer instruction is, how we are going to encode. So I should be able to design a microsequencer to this specification. Presently it's a black box. The second thing is, so this we will discuss in the next class. Following that, if you look at it, if you complete this microprogram, what you will find is there are lots of columns which are compatible. There could be columns which are identical, there could be columns which are compatible. Identical means if the same pattern appears in all the rows, then they are identical. If there are two columns that are identical, do you really need to store them in two different bits of the microinstruction? You can actually collapse them into the same bit. You can take that output and just fan it out. You can give it to both the control signals which have the same column. So similarly, if there are two which are compatible, compatible comes from the don't care part. If you consider, so for example, if you consider this and this particular column and this particular column. And when it is 0, it is 0. When it is here, it was 0, it is don't care. They are compatible. 0, 0, 0. Okay, they are not. Sorry, the 0, 1 is a problem. But let us say this was not a 1. So when this is 1, this is don't care. So if you require a don't care, then you can make them those columns to be compatible. So you can use these facts to reduce the number of columns. When you reduce the number of columns, what are you doing? You are effectively reducing the size of your microinstruction, the number of bits in your microinstruction, which in turn is going to reduce the size of the control ROM as well as the register. So it is a very effective technique so we will talk of some techniques for reducing the width of this by looking at trying to find out which are the columns that are compatible. Again, we can use graph algorithm techniques to do that. Okay, so you can compress this into the number of bits. We will discuss that.